very happy to introduce Adam Bouland. Adam will tell us about something that's seemingly a little different than what we've heard before about tomography, but it's still exploring this, this phenomenon of exponential complexity of quantum states, but this time having to do with quantum gravity and things like that. So Adam, the floor is yours.
All right, great. Yeah, thanks so much for the introduction. So I'll be telling you today about pseudo-randomness and the ADS-CFT correspondence. And this is all based on joint work with Bill Pfefferman and Umesh Vazirani. So the starting point for this talk is a somewhat strange question. It is, could quantum circuit complexity be physical? That is, could circuit complexity be a measurable quantity like heat or light or distance or time? And at first glance, this sounds like a somewhat strange question to a computer scientist. But believe it or not, there's actually been a proposal that circuit complexity is physical in the context of black hole physics. This idea that circuit complexity is physical emerged out of something called the IT from qubit collaboration, which is another Simons Foundation collaboration, but this one on quantum gravity. And this is a giant collaboration with 17 PIs across many different institutions. And the context for this proposal that circuit complexity is physical really lies in one of the central challenges of 20th century physics, which has been the challenge to try to create a unified theory which simultaneously reconciles quantum mechanics and gravity. Now, it turns out that actually formulating a unified theory of quantum gravity has been extraordinarily difficult for physicists. And this is due to several obstructions. The first is certain paradoxes that arise when you consider how quantum mechanics interacts with gravity in the presence of black holes. Maybe you've heard of Hawking's quantum information paradox. This goes back to the 60s. But on top of that, there's also this sheer mathematical challenge of how do you combine two very different looking theories that speak different mathematical languages. Now, one kind of glimmer of hope in this quest to create a theory of quantum gravity has been something called the ADS-CFT correspondence of Maldacena. And this has been really one of the most central attempts to construct the theory of quantum gravity. To give you an idea of just how central this is, this paper to date has over 18,000 citations from the last 20 years. All right, so why are physicists so excited about this? Well, the reason is that this ADS-CFT correspondence is, you can view it as kind of a recipe for constructing a theory of quantum gravity. Okay, so what do I mean by that? Let's unpack this correspondence a bit. So what the correspondence is it's a conjecture duality between a quantum gravity theory, which is living on this left-hand theory, and a quantum mechanical theory, which lives on the right hand. Now, it turns out that the quantum gravity theory happens to lie in something called anti-de Sitter space, and the type of quantum mechanical theory is something called a conformal field theory. This is where the name comes from. But just think of it as the simple duality between a gravity theory on the left, that's the object we want, and a quantum mechanical theory on the right. Now, what do physicists mean when they say this is a duality? Well, what they mean is that there is some dictionary that maps states in one theory to states in the other theory, and operators in one theory to operators in the other theory. So think of these as being like, there's two Hilbert spaces, and there's some sort of map that takes states in one to the other. And the idea is that this dictionary is some sort of homomorphism between the theories. So you can see now why physicists are so excited about this duality. The reason is you can view this duality as a recipe for constructing a theory of quantum gravity by studying its dual quantum theory. So in other words, if you can just understand the quantum theory on the right and look at its image under this dictionary map, that then is a recipe for giving you a quantum gravity theory, this object that everyone has been searching for the last 100 years or so. Now, this correspondence is not something that's been fully worked out. I would say that the dictionary is kind of under construction in some sense. And what I mean by this is that they have several examples of different states that are dual to particular states in each theory, but there's not a general, like, well-defined mathematical construction that just allows you to compute this dictionary. It's rather something that's been kind of calculated for specific and structured instances. Okay, now one challenge that has arisen in trying to construct this ADS-CFT correspondence is something called the wormhole growth paradox, which was first identified by Susskind back in 2014. And while this paradox sounds very scary, it's fairly simple to state in quantum mechanical terms. So this paradox involves kind of the following conundrum. So if you look at gravity theories, gravitational theories admit certain solutions to Einstein's equations, which are called wormholes. These wormholes are basically, it's a black hole that connects two distant regions of space-time that are actually not connected to one another. And the unique property of wormholes is that they are objects in general relativity which never equilibrate. Namely, in particular, they do not equilibrate for at least an exponential amount of time. So what do I mean by that? Well, what happens with this wormhole is that if you naturally time evolve it, the throat of the wormhole kind of stretches and shrinks. And what happens is that the volume of the wormhole, that is this interior space in between the two separate universes, grows linearly with time. Now, in classical general relativity, this growth actually continues indefinitely. Of course, we know once this is living in a quantum theory, it will have to stop at some point because the Hilbert space is finite. But just think of this as a theory that really never equilibrates. On the other hand, the quantum mechanical theory on the right-hand side is believed to have a very different sort of equilibrium property. In particular, this quantum mechanical theory very rapidly equilibrates. You should think of it as being something like a blender that very rapidly scrambles quantum information. So to make this a little more precise, if you say, take a local operator O, and you look at, what's the expectation value of this local operator O of the state over time as you time evolve the quantum mechanical theory, what you end up finding is that it equilibrates very rapidly. So it just saturates to kind of its limiting value in a time which scales, say, polynomially in the number of qubits in the system. Okay, so this is a bit weird. This is saying there's some sort of mismatch between the equilibrium properties of the theories. And this is precisely this paradox that Susskind then asked. Susskind asked, what quantity on the right-hand side then could possibly be the dual quantity to wormhole volume, right? If you believe this dictionary exists, there's this full homomorphism between the theories. So everything on the left-hand side should have a dual on the right-hand side. So what could be the dual to volume? What's a quantity of the right-hand side state that should grow with time in the same way as volume? And we know that it can't be any locally defined quantity because those things just equilibrate too rapidly. Okay, so this was the wormhole growth paradox. And in the same paper in which Susskind identified this paradox, he also proposed a solution to the paradox. In particular, his proposed solution was that circuit complexity is physical. In particular, he conjectured that the dual to wormhole volume is literally the circuit complexity of the dual quantum state. That is to say, the minimum number of gates needed to prepare the state starting from some reference state. Okay, so this is a very creative proposal. And it's worthwhile kind of examining, what was the intuition for proposing this as the dual? Oh yeah, I should also mention this proposed duality is usually called the complexity equals volume conjecture because it's conjecturing the complexity of the right-hand theory is dual to the volume of the left-hand theory. So it's helpful to understand Suskind's intuition for positing this as the dual. And the intuition here went something like this. So these states are all evolving according to some Hamiltonian h. And the state of the system on the right-hand side at time t, is given by the usual time evolution of the system, just e to the iht times some initial state psi, which is, say, the initial state corresponding to a wormhole of zero volume at time 0. So you can think of this evolution with time as just applying some fixed unitary u to the state over and over again. So Susskind's intuition was that the complexity of the state relative to the initial state should grow linearly with time, essentially because there shouldn't be any shortcuts to preparing the state other than just applying u, many, many times to the initial state. So that's the intuition here. Now, there's been actually some work trying to provide supporting evidence that this could be a reasonable conjecture. So for instance, there was some interesting complexity work of Aronson and Brandau and Bodanowicz and Balasubramanian et al., which showed that basically, it is plausible that for certain unitaries u or Hamiltonians h's, that the complexity of the states should grow at some rate with time, of course, under certain complexity theoretic assumptions. Similarly, there have been some works on the gravity side as well by Stanford and Susskind, Stanford and Schenker, and others, who tried to show that some of the behavior of the volume mimics what happens on the complexity side as well. And I'll discuss this evidence a bit more. But that's kind of the state of evidence for this conjecture. Now, in evaluating this proposed solution as a computer scientist, this solution might strike one as somewhat strange, because as computer scientists, we know that circuit complexity is a very subtle quantity to try to pin down. If circuit complexity were easy, we already would have shown NP is not NP/poly. And moreover, we know that there are certain barriers to, say, separating P versus NP, which actually tell you that circuit complexity is something that's very difficult to feel or estimate. So it seems strange to be equating circuit complexity with a kind of very physical quantity like the volume of a wormhole. All right, so let's see if we can formalize this computer scientist discomfort a bit more carefully. I think the best way of understanding this is, this discomfort is really that there seems to be some sort of tight mismatch between complexity and volume. So namely, on the one hand, circuit complexity is something that should be very difficult to feel or estimate, right? This is our intuition coming from, the study of computational pseudo-randomness, which I'll bring up in a moment. And the second source of our discomfort is that, this wormhole volume sounds like something that should be easy to estimate. Like, it kind of sounds like something like naively you should be able to jump in the wormhole and just kind of get out your tape measure and then kind of measure the wormhole volume. So it seems like something that has a very different property, namely that it's easy to estimate. So it seems that these properties are a bit mismatched across this duality. But it turns out that formalizing this discomfort is surprisingly tricky. This is for kind of two reasons. The first is that only a very special subset of quantum states are being considered in this particular conjecture. It's not, say, all quantum states on that Hilbert space. It could be that the complexity of these states that they're talking about is somehow easier to estimate than for generic quantum states, right? So that would kind of be an obstruction to formalizing this discomfort. Moreover, there's a second obstruction, which is coming a bit more from the physics side, which is that no single observer in the black hole can actually estimate the volume. So there actually is no way in which a person can jump into the wormhole, take out a tape measure and kind of measure how big it is inside the wormhole and then give the answer. This is due to certain constraints in general relativity, which basically say that once you jump into the wormhole, you die in some constant amount of time. So you don't have enough time to kind of perform any experiment that would allow you to measure this wormhole volume. So maybe the second quantity is something that's inaccessible as well. So in this work, what we did is we started with this discomfort and we asked, can these objections be realized in this model? And if so, what would this mean for the ADS-CFT correspondence? And this is precisely what I addressed in joint work with Bill Pfefferman and Umesh Bazarani last year. In particular, we showed two results. So our first result is that we created a form of computational pseudo-randomness in this dual quantum theory, that is in this tiny subset of states that are being addressed by this complexity equals volume conjecture. And the basic idea here is that what we ended up creating is some sort of ensemble of states within this domain of validity of the conjecture, which are extremely difficult to distinguish from one another, but which have very different wormhole volumes, right? Now, an interesting aspect of this construction is that it actually applies to any quantity that grows with time. So what do I mean by this? Well, once you have a pseudo-randomness construction, it actually implies not only that the circuit complexity of these states is hard to estimate, but moreover, any quantity that measures kind of how long you've acted on the state is also something that's difficult to measure as well. So what this means is that this pseudo-randomness barrier that we're creating is not just an obstacle to having circuit complexity as the dual, but it's actually an obstacle to any quantity you would posit as the dual to volume. And this was something that maybe surprised us when we were going through this work. We maybe initially thought that this pseudo-randomness thing was going to only affect circuit complexity as the dual. It turns out it's much more general than that. So this means that somehow this discomfort we're feeling about positing circuit complexity as a dual is inevitable. It's not something that one can escape by kind of just picking a different dual quantity. The second argument is that we showed that the wormhole volume is something that is easy to compute. Now, this is, when I say easy to compute, I mean this in kind of a little more general of a setting. Actually, arguing the volume is easy to compute requires combining the experiences of many different observers who live in the wormhole and kind of post-processing what they saw in order to kind of infer the volume of the wormhole from their kind of collective or aggregate experience. So now from a computational side, this is something that makes sense, like you can run different quantum experiments and post-process results. This is, an efficient model of computation. So, but this is kind of a non-physical experiment in that the wormholes whose experiences, the observers whose experiences we are combining are not people who could have talked to one another physically within the theory. So kind of the volume here is easy to compute in a computational sense, even though it's kind of physically inaccessible. So what does this?
Yeah, sure. Question from Q&A from Viraj.
Sure.
He asks, how many observers? I think it's maybe.
How many observers? Polynomially many observers. Yes, that's a good question. The number of observers will end up being just kind of proportional to the length of the wormholes we're talking about. But in all of these constructions, everything will be in polynomial time. So we aren't talking about very late time wormholes. These are wormholes that have only evolved for a relatively short amount of time. Yeah, that's a good question.
And the parameter here is like the number of, you said the length of the wormhole.
Yeah, and the number of observers you need ends up being, in some sense proportional to the length of the wormhole. But the, things are a bit more subtle than that, but I think that's the overall picture. It depends a little bit on how you imagine this quantum gravity state encoding the bulk geometry. This is kind of taking a very conservative position where you say, okay, I have no idea what ADS-CFT looks like, but it should at least tell me what would happen to a single observer. Like, you might hope that it's more general, that it allows you to reconstruct the entire space-time, like the way you would simulate GR on the quantum computer, like, where you say could learn the metric at every point in space. If that were the case, if ADS-CFT encoded geometry in that more general way, then you would only need one copy, and kind of the second part of our argument might not be necessary. Okay, great. So I'll get to these arguments in a little more detail soon, but let me just quickly tell you kind of what this means for ADS-CFT. So, kind of the first part of our results argued that kind of, whatever this dual quantity to volume is, it has to be something that's really difficult to compute, something like complexity. And here we mean exponentially difficult to compute even with a quantum computer. On the other hand, we argued that if you had the gravity state on the left-hand side, the wormhole volume would be relatively easy to compute. That means that, in other words, it would be computable in polynomial time given access to a quantum computer. So what does this imply? Well, this implies that this dictionary map is reducing a problem that's very hard on the right-hand side to a problem that's very easy on the left-hand side, right? So that means, something here has to be doing the heavy lifting. So in particular, this means that this dictionary itself then must be exponentially difficult to compute. This would be like, if you gave a reduction from, 3-sat and you showed that 3-sat is reducible to a problem that's in P, okay, yeah, possibly you could have shown P equals NP, but more likely you made a mistake and somewhere in your reduction, you accidentally perform some exponential time computation. This is kind of what's going on here, because this duality is reducing a hard problem to an easy problem. Right? Now, what this means for ADS-CFT kind of in general and kind of interpreting this result is something that I'm going to address more in detail at the end. But I just wanted to give you a quick flavor of kind of where we're going with this, so that you're kind of able to see kind of how the argument is stitching together to get some conclusion about the complexity of ADS-CFT. So in some sense, yeah, so you could say that our result might be saying this dictionary is permanently under construction, in the sense that yeah, it will be possible to compute for individual states or particular structured instances, but this general dictionary should be something that should be extremely difficult to work out. Okay, so now my remaining time, I'm going to try to do some of the key ideas that go into this argument. In particular, I'm going to try to explain to you the ways in which we establish pseudo-randomness within the domain of validity of this conjecture in the CFT. And this is a very interesting kind of argument because it ends up bringing together a lot of different notions, both from classical computer science and pseudo-randomness, and also from cryptography. Actually, it turns out that block ciphers will play a role in establishing our pseudo-randomness argument. All right. So in order to try to establish pseudo-randomness for these CFT states, we first need to understand what states are we allowed in the CFT to begin with. So what is this kind of domain of validity of this conjecture? So in order to understand this, we're going to start with a toy model in which we're going to model the CFT as a system of n qubits, where n is the entropy of the black hole. Now, it's true that a conformal field theory is not naturally a theory that is a tensor product of qubits. That actually it's an uncountably infinite dimensional. We make a very concrete model so that then we can then argue about it more specifically. And this particular model is something that has already been used in the ADS-CFT literature. So the initial state of our system in the CFT is a special state called the thermofield double state, which we denote TFD. And this is a low energy state of the Hamiltonian. So it's not an eigenstate, but it's a state that its expected value of its energy is relatively low. Now, the structure of the state is not very important for our arguments. So let's just say for the moment that it's just some state that's relatively easy to prepare. Now, this quantum state, this special state TFD, evolves according to the CFT Hamiltonian. So this is kind of the set of states that are allowed in the CFT. If we want to look at it in this discretized picture, it turns out that this Hamiltonian has an additional special property, which is that this Hamiltonian is believed to be scrambling, which is to say there's some characteristic time scale T naught, such that after evolution for time T naught, this Hamiltonian kind of diffuses local perturbations throughout the system. So let's just call it evolution by a scrambling time U. So the states in the theory, just with normal time evolution are just, you just apply U over and over again to this initial state. Now, formulating complexity equals volume for just these states, seems like a very kind of narrow theory. So actually, complexity equals volume is formulated for a bit of a more general subset of states. Namely, the evolution is also allowed. Sorry, I don't know why the animation's not working, but namely, this evolution can be perturbed by inserting some small number L of single qubit gates into the evolution. And the idea is that each insertion of a 1 qubit gate, would increase the energy of the state by some small amount, say, assuming this Hamiltonian HCFT is local. And what these local 1 qubit gates in the CFT correspond to is these correspond to shocks in the gravity theory, which kind of are, what these shocks do is they throw energy into the wormhole. So these are sometimes called shocks or shock waves that we're applying to the state. So what we end up getting is some state that looks like the following. We start with the TFD. We evolve for a scrambling time. We then apply a 1 qubit gate O1. We then evolve by U again. We apply another 1 qubit gate O2, et cetera, et cetera. And let's say we do this L times. So what these states are is, they're basically like the normal time evolution, which you obtain by just applying U many times to the initial state. But you're allowed to make some perturbations in this circuit. Namely, you're allowed to apply some 1 qubit gates kind of sprinkled throughout these applications of U. And this is the precise set of states that are allowed in the CFT, and that to which their circuit complexity is conjectured to be dual to their volume. Now, the evidence, somewhat surprisingly, quantum gravity theorists were able to show that actually the changes to the wormhole's volume, which are induced by throwing in these shock waves, actually exactly matches the changes of complexity that one obtains in these states by adding these 1 qubit local operator insertions. Actually, this even holds in a bit more general model than this, where you're allowed to apply U inverse as well as U in this kind of time evolution. So this is kind of really surprising when you first see it. And this is really where their evidence for complexity equals volume is coming from, is that, like this kind of somewhat miraculously, this general relativity calculation of what happens to a wormhole when you throw in energy to it ends up kind of mirroring exactly what happens when you evolve by some Hamiltonian and insert some 1 qubit operators into the Hamiltonian evolution.
Adam, there's a question in the Q&A.
Yeah, sure.
And I think, John, you're unmuted, so you can talk.
Sure, yeah, I just want to ask, okay, so as you know, not all circuits are hard to compute, just most of them. So how does this factor into the theory? Are there corresponding trivial wormholes whose volume doesn't grow with time? And is it known that these are a vanishing fraction of all wormholes?
In ADS, so this is really talking about this particular state and this particular type of two-sided wormholes. So yes, there are, wormholes always have more than one side, but there are one-sided black holes that do not have this sort of volumetric But for one-sided black holes, which are the ones that form from gravitational collapse, like the ones we think exist in our universe, these ones, there is no other side to it. There's just a singularity on the other side. So there is no other universe you could reach. But I think your question though is getting at kind of an important point, is that what's happening here. Like the reason that we're limited in the number of shocks we're allowed to apply to the wormhole, which is the number of 1-qubit gate operations, is because each of these kind of adds some energy to the wormhole. So one's worried if you threw a lot of energy in that you could, completely distort the geometry, right? So this is why we're limiting ourselves to, kind of applying, adding a very tiny amount of energy to the system. It's not even clear if there is even a well-defined geometry on the other side if you throw in too much energy. Yeah. Great. Yeah, thanks for the question. Okay, so these are the sets of states that are allowed in the CFT. So the central question we're going to be asking is, how hard is it to estimate the circuit complexity of such states? So we have states of the following form. The question we're going to be asking is something like this, given many copies of the state of the above form, how difficult should it be to estimate its circuit complexity, which here ends up being roughly the number of times that you applied U, right? Plus some tiny correction factor for these extra 1-qubit gates. Now, the standard tool that one would usually turn to try to answer this question would be to try to show that states of this form a unitary T design, right? So if states are a unitary T design, then this means they're information theoretically indistinguishable from, say, T copies of a Haar random state. T copies of these states would be indistinguishable from T copies of a Haar random state. And that would immediately imply that the complexity of these states is hard to estimate because these states have low complexity, but Haar random states have maximal complexity. Now, unfortunately, it turns out that we can't use this tool in this to address our question. The reason is that the number of different states we have in our ensemble of states we're talking about here is something that's relatively small. It's like 4 to the L states, but L has to be much smaller than the number of qubits n. So we have think of L as being like n to the epsilon for a tiny epsilon. Whereas on the other hand, there's a very simple counting argument that says if you want an ensemble of states to be a 1 design, they need to be 4 to the n different elements in the ensemble, kind of analogous to how the Pauli group is a 1 design. So in some sense, information theoretic tools will not work to address this question. So instead, to address this question, we're going to use a different technique. We're going to use the tool of computational pseudo-randomness. So computational pseudo-randomness is basically the computational form of information theoretic pseudo-randomness, where we're going to try to argue that even though these states are information theoretically distinguishable from random, we'll try to argue that the information is somehow inaccessible to limited time computations. So fortunately, this notion of quantum computational pseudo-randomness was actually defined in previous work of G, Liu, and Song. So in particular, they define this thing called a quantum pseudo-random state ensemble, or PRS. And the definition looks something like this. Like you call a collection of states psi k on n qubits, where k is, say, an n-bit bit string. Think of k as being your secret key. So you call a collection of these states a PRS if it obeys the following 2 conditions. The first is that they're efficiently preparable. So in other words, you can create each state psi k in polynomial time, with a quantum circuit starting from some reference state. And the second is a computational indistinguishability criteria, which says something like this, like for any polynomial q of n copies of the state psi k for a fixed but random k are not BQP distinguishable from q of n copies of a Haar random state phi. So this is saying that kind of, even though our key is of fixed polynomial size, even if I gave you an arbitrarily number, an arbitrarily polynomially scaling number of copies of the state, if you just had access to efficient quantum computation, you wouldn't be able to distinguish it from that many copies of a hard random state. So this is clearly, just the quantum analog of, the classical notion of a pseudo-random function. And what's really nice is that, G. Leon Song and also recent work of Berkeley and Shmueli showed that there is a way of efficiently creating quantum pseudo-random states if you have access to universal quantum computing. So in particular, they showed something like this, like, let's say you have a pseudo-random function f k of x keyed by some secret key k. Then if you consider the state, which is an equal superposition over all strings, and you just apply a pseudo-random phase to each string, then this ensemble of states is actually computationally indistinguishable from a hard random state, even with arbitrarily polynomially many copies of the state. So in other words, so long as you believe that there is a PRF that's secure against quantum computers, say like you believe LWE, or as long as there's some one-way function hard against quantum computers, we know this can be constructed. Then this means that you believe it is possible with universal quantum computers to prepare pseudo-random state ensembles. Okay, this is really great, but in some sense, this work doesn't directly help us. So the CFT states that we're talking about here, are not states in which it seems to be possible to perform universal quantum computation, right? Like they're states, in some sense, our hands are really tied with these states. All we can do is apply some fixed unitary U, which is known to everybody, and apply some small number of perturbations of that evolution. So as a result, this means that we cannot use the JLS construction, kind of because the set of states we're talking about here is just too restricted. All right, so how are we going to get around this? Well, instead, we're going to take a very different sort of inspiration here. We're going to take our inspiration from block ciphers, such as the AES and DES crypto systems, and we're going to try to use our intuition from block ciphers to create a quantum PRS ensemble with our very limited subset of states. All right, so here's our pseudo-randomness construction. The intuition is fairly simple to explain. So, all right, first let's observe that, even though our unitary U, which, is scrambling in some sense, like, it kind of mixes up the whole system, diffuses local perturbation throughout it. The state that you obtain by just applying many times to this initial state, this is not a pseudo-random state. So, how can you see that? Well, this is because this Hamiltonian HCFT is actually fixed and kind of known to everyone. So as a result, if you were given a state of this form, you could just time evolve it backwards to try to, until you hit the initial state in order to determine the length of the time evolution. So in other words, in this model, the adversary has the ability to apply U inverse. So it doesn't make any sense to, to not add any perturbations here. So the key idea in our construction is to apply the shocks to the state, apply these 1-qubit perturbations, but don't reveal them to the adversary. So in other words, treat the pattern of shocks as kind of the secret key that we're using in our construction. And the basic idea is that the shocks that you're adding in can help obscure the length of the time evolution of your system, because it means that just running U inverse backwards no longer will get you to your initial state. So that's kind of very hand-wavy. So let me formalize this a little more carefully. So let's say we pick a secret key K, which is in the poly group. So let's say instead of the secret key K being a bit string of length L, let's say it's a string in IXYZ of length L, right? And let's consider states which are obtained by alternating applying U and applying the IF poly operator in the secret key. So, and let's just say that we're always applying those operators to the first qubit for simplicity. The basic idea is that applying these 1 qubit operators, these 1 qubit unitaries, creates kind of branching points in the evolution of the system. So in other words, if you start with your initial state, this TFD state, there are now 4 different states you could evolve to in the next kind of step of the evolution, and then 16 going on, et cetera, et cetera. So there end up being 4 to the L different states that you could reach by one of these, shock patterns. And the basic intuition is that, if you were hard random, then all the states in these trees would be approximately orthogonal to one another, right? And what's the reason for this? This is just kind of some sort of simple calculation, which is like, if you take a hard random state and you apply a poly X on the first qubit, we know that that renders the state nearly orthogonal to itself, right? This is just a property of generic states. So the claim that we're making in our paper is that this is a pseudo-random state ensemble, essentially because if I gave you an unknown state phi, it would be very hard to tell if the state phi I handed you is a state that lies in this tree or not, right? So okay, and this is, again, a bit loose, so let me be even more precise. So the way that we argue for security is in a simplified black box model. So in particular, let's suppose that our unitary U were truly random. Later we'll argue this could be instantiated in some sort of pseudo-random way, but let's just assume it's truly hard random for now. And let's imagine that the only access you have to U is by applying U and U inverse as black boxes. Then our claim is that in this black box model, the number of queries that you need to distinguish a random psi k from a truly random state scales exponentially in L, right? And the intuitive reason that this is true is that this effectively just ends up being some sort of search lower bound. The basic intuition is that if this tree is relatively shallow and you have a truly random unitary, then all of these states in the tree are essentially like independently random states chosen, essentially independently random states chosen from the Haar measure over this distribution. Because effectively the tree is too shallow for you to see any collisions in it. So this is kind of our evidence for security. And we conjecture that this security holds in the white box model, where this unitary U, isn't truly random, but instead it's, whatever the scrambling dynamics of the CFT are. And of course, we can never prove a conjecture like this. And also we don't even have an explicit description of a Hamiltonian to work with for the CFT Hamiltonian. But this is the basic idea of the construction. And, to see this a little more concretely, it might be helpful to show there's a much simpler kind of classical analog of the pseudo-random state construction. And I think that understanding this classical analog might make understanding this argument a much more straightforward. So the classical analog is something that I'm going to call the flip or not block cipher. And you'll see why I'm calling it this in a second. So in this, so what this block cipher is let's just think of it as a way of generating strings pseudo-randomly. So let's say that we have a fixed but random permutation sigma of n-bit strings. And let's pick a secret key, a bit string of length L. So let's imagine the following process. Let's imagine we start with the string 0 to the n, and then we apply sigma. And then we according to the first bit of the secret key B, flip the first bit of the string or not. So if the first bit of the string is 1, flip the first bit after this first application of sigma. And if it's 0, do nothing, right? And then apply sigma again, and then flip the first bit of the string according to the second bit of B, et cetera, et cetera. So let's say that we iterate this L times. This is a particular way of generating strings. And you can see that this looks very analogous to our quantum pseudo-random state construction, right? Because these unitaries, our unitaries U that are very scrambling are now replaced by random permutations. And instead of applying poly operators, we're just flipping the first bit of the string. Now, let's suppose that I gave you a string Y. One might ask, how hard is it to tell if Y was either given to you, generated by this process for a random bit string B, but you don't know the bit string, or Y was uniformly and independently random. So it has nothing to do with either sigma or B. So it turns out that you can show very rigorously that if you're only given black box access to sigma and sigma inverse, then you need at least 2 to the order L/2 queries to the black box for sigma and sigma inverse in order to distinguish one of these random strings YB from a truly random string. Right, and the intuition here is exactly as before, right? Like the intuition is that this process is generating some sort of tree of possible strings you could be in, and if this tree is shallow enough, that's if L is much less than N, then this tree is basically independently random strings. So it ends up reducing to a sort of unstructured search problem. So this is the black box security statement that we prove rigorously. And in the quantum setting, we sketch a proof of it, but we don't give the full proof because it turns out some of the details end up being quite nasty there. But this is kind of the classical intuition for the pseudo-randomness construction of our scheme. And actually, yeah, sure.
There's a question from the Q&A. Vinod, do you have a question?
I think Adam actually answered it. The theorem statement says the sigma and sigma inverse are given via black box access. That was my question. Thanks.
Yes, exactly. So this is shown in a black box model. Think of it like a random oracle model.
Yep.
Sigma
Yep.
is a random oracle.
Yep,
Or in this case, a permutation. Yeah.
Yep.
But,
thanks.
Yep. Well, with polynomial queries, of course, random permutations and random functions are
That's right. Thanks.
Yeah.
Adam, I had a kind of a basic question. So maybe you talked about this earlier. So this CFT Hamiltonian, you seem to assume that it's scrambling.
Yeah.
What is this just believed to be true, or is there some principled reason for why we believe it should be scrambling?
Yeah, that's a great question. So this is something that has been discussed in physics for a long time, but there's this thing called the fast scrambling conjecture, which basically conjectures black holes are the most efficient scramblers in nature. I'd say this is something that's very highly believed by the community, and kind of the reasons it's plausible maybe go back to kind of Hawking's original black hole information paradox, which maybe I don't have time to explain. But I'd say this is something that's very widely believed by the community. If given a suitably rigorous definition of scrambling. Of course, there are many different definitions of scrambling here. I'm being somewhat intentionally vague here, but the fact that there is some scrambling behavior is not something that I've heard being debated in the physics realm.
So it would be correct to somehow equate CFTs with black holes, like that's somehow the...
Well, in some sense, like this ADS CFT picture is trying to give a more understandable picture of what happens to a black hole as it kind of gains quantum information as stuff falls into it and then loses quantum information through Hawking radiation. So somehow there's some paradoxes that would come up if the Hawking radiation, if the output of the black hole, which is kind of the analogy to the CFT dual, if it were not scrambled, then there would be some kind of immediate paradoxes that would arise where there'd be a copy of some infalling quantum information both on the inside of the black hole and kind of on the outside of the black hole simultaneously. And I'll maybe get to how this kind of fits into our work recently, but if it's kind of scrambling, it could be a little more plausible because somehow maybe the information is there, but you can never access it. But I'll explain this a little more shortly.
Okay, thanks.
Yeah. Sure. So yeah, but anyways, I wanted to say that these kind of flip or not block ciphers actually look very similar to block ciphers like AES. So if you compare our construction, where you're applying some permutation sigma and kind of applying the first bit of the secret key and then kind of applying sigma and then applying a bit of the secret key, this looks very similar to block ciphers like AES, where here they have some kind of very scrambling permutation of sigma, but instead of applying the secret key kind of one bit of the time, they tend to like XOR in the entire secret key to every bit of the string at every round of the block cipher construction. So you can kind of see our pseudo-randomness constructor that we made is kind of like a block cipher like AES, but where you dribble in the secret key one bit at a time instead of kind of applying it fully at each round. So in this sense, you can kind of think of our result as giving a kind of fully quantum block cipher in some kind of hand-wavy sense. Okay, so in short, yeah, so I'm just going to quickly kind of summarize with what we showed in the pseudo-randomness parts. So in short, we argued that the states in the CFT are plausibly pseudo-random, assuming you're willing to make our white box security conjecture. And the scrambling nature of the CFT evolution is what makes our white box security conjecture plausible in this construction that's inspired by block ciphers. And this pseudo-randomness statement can be easily seen to immediately imply that estimating the length of time evolution of the dual quantum state is something that's exponentially hard, right? To see this, you just imagine instantiating our construction with different polynomial lengths of time evolution. And if each of these different lengths of time evolution are indistinguishable from Haar random states, well, that means in particular, they're also indistinguishable from one another as well, right? So this ends up establishing that different instantiations of our construction with, say, wormholes of length n squared versus n cubed should also be computationally indistinguishable from each other. And also, kind of as I mentioned earlier, this pseudo-randomness argument shows any quantity that grows linearly with time of this quantum state is something that's hard to estimate, right? Because, again, if you apply u n squared versus n cubed times, this is not something that you can efficiently distinguish. So on the other hand, there's the second part of our paper, which is arguing that the volume of these states is somehow easy to feel. And I don't have time to get into this in detail, but I'll kind of sketch the argument for you again. It's our pseudo-randomness argument really tells you that getting even a really coarse estimate of the volume, like is it n squared or n cubed, would already be enough to break our pseudo-randomness construction through the dictionary. But as I mentioned, no one observer can mention the volumes. So our basic argument is that if you create polynomially many observers in this wormhole, which are spaced such that kind of if there's a horizon between them, they cannot communicate but with one another. But if there is no horizon, then they can communicate with one another. So you just kind of throw a bunch of observers into the space and kind of count how many of them were able to talk to one another. Then it's quite clear that kind of post-processing their outcomes of whether they were able to communicate with their neighbor ends up giving one a very coarse estimate to the volume of the wormhole. And an interesting fact to note is that in order to make this argument that we can perform this post-processing, we have to assume a quantum extended Church-Turing thesis for quantum gravity. That's because we have to imagine that you could kind of separately simulate the experiences of each observer with a quantum computer, and then on top of each simulation, kind of apply a polynomial time post-processing step, which kind of aggregates their experiences, and then outputs this bit, which tells you, was the volume of the wormhole small or large. So the fact that we have to extend the quantum extended Church-Turing thesis for quantum gravity is kind of a very interesting aspect of our result. So, as I said before, this argument implies that the dictionary is exponentially difficult to compute, there's actually one other way that you could evade our arguments. Another possibility that our arguments raise is that it could be that the quantum extended Church-Turing thesis is false in quantum gravity. So if actually the quantum gravity dynamics of the interior of a wormhole are exponentially difficult to compute with a quantum computer, then it wouldn't necessarily be the case that the dictionary would have to be hard to compute, because this kind of simulation of the experiences of the different observers is an integral part of our argument. So let me just kind of quickly conclude with a few kind of high-level comments as to what our results might mean for ADS-CFT. So I think that the jury is still out here, but there have been kind of a few different flavors of interpretation of what these pseudo-randomness statements might mean for the field. The first flavor is maybe best expressed in a recent paper of Susskind, who argued in some sense that the complexity of the dictionary, you could think of it as a bug. Maybe it's not a bug, but it's something that should be hidden, and it's something that should be hidden behind horizons. So one thing to note is that in order to get a contradiction with our theory, you have to simulate the experiences of observers inside the horizon of the black hole. That's to say, observers who jumped in. So Susskind conjectured that maybe this is reflective of a broader trend. Maybe there's a form of computational cosmic censorship in which, in our universe, any violations of the quantum extended Church-Turing thesis or exponentially complex dictionaries are always shielded by horizons. That is, these kind of pathological computational things can only occur kind of after you jump into a black hole. And this can be seen as kind of a computer science analog of the cosmic censorship conjecture of Penrose going back to the 60s, who conjectured that all singularities in general relativity are shielded by horizons. This is kind of a computational version of that. Now, there's another way of viewing this result, and this is maybe best expressed by a recent paper of Kim, Preskill, and Tang, which is you could actually view the complexity of this dictionary as a feature rather than a bug. So in particular, this high complexity dictionary might actually protect causality in these theories. So as I was mentioning before in the answer to Kai Henry's question, you might think of this CFT state as kind of being similar to the Hawking radiation that was emitted by a black hole. Now, if you believe in some kind of holography or some kind of complementarity picture of black hole physics, then you believe that the exterior physics of the black hole are in some sense dual to the interior physics. So there is some sense in which the physics outside the black hole and inside the black hole are related to one another by some dictionary. And what Kim, Preskill, and Tang raise is that, well, maybe the fact this dictionary is exponentially complex is what prevents you from having some lack of causality in your theory. Like if this dictionary were too simple, then someone could manipulate kind of the boundary theory or the Hawking radiation that's very far from the black hole in order to manipulate the interior of the black hole, which is far, far away, and that would be something that would be seen as kind of pathological in the theory. So it could be that this high complexity dictionary is actually something that might be helpful or beneficial to ADS-CFT. And finally, there's this question about, what would a quantum extended Church-Turing thesis mean for quantum gravity? We kind of use this extended Church-Turing thesis as a black box to say we can simulate the experiences of observers. But, formulating this a bit more rigorously is something that I think is, could be a really interesting problem to work on. It would require answering problems like, how does this quantum gravity state encode the geometry of this theory? And so, there's some interesting physics questions there, and there are also some interesting computer science questions there into how you formalize computation in a relativistic theory. So yeah, so that's it for my presentation for today. Thanks so much for your time and attention.
All right, thank you very much, Adam. That was a super interesting talk. Yeah, so people, please, if you have any questions, you can type it into the Q&A or in the chat. So John would like to re-ask his question from earlier.
Sure. Can you remind me of the question?
Yeah. Sorry. Yeah, I just got a little confused. Basically, okay. As I understand it, there's this connection between wormhole volume and like the circuit complexity, and kind of the intuition is that, well, circuit complexity, as you apply this unitary t times, the complexity grows by t, which is similar to the wormhole volume, which also grows by t. But it's basically the case that like most circuits are difficult to compute, but some of them, a small fraction of them are easy to compute. And I was curious how this factors into the theory.
What do you mean by some circuits are difficult to compute?
Well, my understanding, it's like you're thinking that this unitary u, maybe as you apply it t times, the circuit complexity grows linearly with t.
Oh yeah. That's not something that would happen for all unitaries u, of course.
Yeah. So how does that is there some sort of correspondence on like the wormhole volume side that's natural?
Oh, that's a great question. So I'm not sure that the dictionary is as well worked out as maybe you're thinking here. In the following sense, I'm not sure that I think what there actually is there's one fixed Hamiltonian that they're really talking about on each side. I'm not sure that there is necessarily freedom to consider different Hamiltonians on one side versus the other here, if that makes any sense.
I see. You're saying there's like, it's not like any Hamiltonian they're just like one kind of universal wormhole.
There's one, and they think it should be scrambling in some way.
I see.
And okay, so we're working with that. Now, there has been this complexity theoretic work that I alluded to of Aronson and Brandau and Bodanowicz, who showed that if you somehow encodes the steps of some universal cellular automata or something like this, then after some exponential amount of time, you should be able to do p space in this model. So unless p space is equal to BQP, then there should be some super polynomial growth over time. Those are kind of the flavors of the sorts of complexity theoretic evidence that's been provided so far. But those are all saying like, here's some super specially constructed Hamiltonian. Let me show that it's plausible that complexity grows here. But there's not like an explicit Hamiltonian that they have written down for you to ask, does this Hamiltonian meet this criteria or not?
Okay, thanks.
Yeah, sure.
You want me to comment briefly on that?
Yeah, sure.
I think, okay. I mean, I think it getting the complexity growth is actually a pretty generic property, of these Hamiltonians. In particular, like basically anything that is sort of computationally universal, we could use it in our argument. So sort of anything that can, such that sort of simulating its evolution over an exponential number of steps is a p-space complete problem, right?
Yes.
But that's like a pretty generic property of dynamical systems, right? Now, we know that some property has to be needed. I mean, just as John was saying, like if we had a zero Hamiltonian that did nothing, well, it's never going to generate any complexity, right? So you do need something about the Hamiltonian, also something about the initial state that it's acting on. But I think
it's not an eigenstate or something.
Right.
But trivial.
And it's it's very much related to what Dorit and Yossi Atiyah called the no fast forwarding property in a paper that they had a few years ago, right? And and the conjecture that they made there is that like if you take a generic Hamiltonian, it should not be fast forwardable. That is, there should not be an efficient way to predict what it will do after an exponential amount of time. And basically, we just, I agree with their conjecture that sort of most Hamiltonians should be non-fast forwardable, because of being computationally universal, probably, right?
Sure.
Therefore,
now, of course, Whether the CFT Hamiltonian has these properties is a little unclear, but I guess one might argue, well, it should be capable of, some form of universal quantum computing. So presumably it has a universality property along these lines, right?
Yeah, I mean, you could say that maybe anything that is so simple that these results wouldn't apply to it is maybe also so simple that it would not be a good model for our universe.
Yeah, it might not be rich enough to capture the physics that they want. Yeah.
Yeah.
Yep. Yeah. Thanks for the comments.
Question from Isaac Kim. Isaac, I think you can.
Yeah. So I wrote it up already, but I'll just repeat. So when you argue that the wormhole volume is easy to compute, how would this conclusion change if the number of observers you can put in the wormhole is like little o of n? And I asked this question because if you have sort of too many observers, you end up like injecting too much energy into the wormhole, which may actually change the underlying geometry.
Yeah. So first of all, we don't actually need any mass or we don't need a physical observer there. We just need some way of kind of measuring whether some photon reach some state, reach some place or something like this. And there's no need for all the experiments to happen simultaneously as well. So I don't think this would necessarily be a barrier to the argument. You just have to imagine doing the experiment pairwise rather than throwing them in all at once, right? So this would just blow up the number of copies of the state you need, but then you wouldn't actually need to instantiate all of them in one copy of the state. So yeah, there could be some trade-offs here between the number of copies of the wormhole state you need to estimate the volume and the number of observers you throw in.
Okay, thanks.
Yeah, and of course, as I mentioned earlier, if the state actually just encodes some global geometry, then you don't even need this argument, right? So it somewhat depends on how strong of a complementarian you are in terms of believing you can only reconstruct single observers' experiences.
Okay, thanks.
Yeah, thanks.
Any other questions? Okay, so if not, thanks, Adam, and thanks to all the speakers of today's session. Yeah, I think that today was pretty successful. I think we averaged around like 80 or so participants throughout the day. So that's pretty awesome. We'll continue tomorrow at 9 a.m. Pacific time. So thank you all for tuning in. Bye.
Thanks.